The proposed method for integrity verification of measured transformer currents is suitable for the modular development of hardware-in-the-loop digital twins, HIL DTs. It utilizes the Adaptive Extended Kalman Filter to estimate the parameters of transformer currents, which can be non-sinusoidal during transients such as transformer energization. The method is evaluated using EMTP-RV for simulating transformers and Matlab for executing the proposed method. The simulation results demonstrate that the method is able to accurately estimate and closely track the current measurements. The proposed method employs a recursive method for integrity verification of measured transformer currents, which is suitable for the modular development of HIL DTs. The differential equations, DE, describing transformer transients are relatively complex, requiring the use of numerical DE solvers with small time steps. This implies that replicating transformers with HIL DTs requires a continuous flow of accurate measurement samples with a high sampling rate. The paper presents a method for estimating the parameters of a transformer current using an Adaptive Extended Kalman Filter, AEKF, and a noise parameter estimator module. The current parameter estimator is the first module, which processes a measured sample of transformer current to estimate the magnetization current and the core loss current. The noise parameter estimator module estimates the measurement noise covariance matrix using the residuals between the measured and estimated currents. The advantages of the proposed method are as follows. 1. It is able to estimate the parameters of measured currents even when the transformer is heavily saturated. 2. It is computationally effective owing to its recursive mathematical formulation, which is suitable for implementation in industrial computers. 3. The proposed method adaptively modifies itself with respect to measurement noises, which increases its accuracy and trackability. The paper presents a novel approach to estimating the magnetic flux linkage in transformers using the Augmented Extended Kalman Filter (AEKF) method, which handles the nonlinearity of the transformer's magnetic circuit and uncertainty in measurements. The AEKF method combines the measurement of the transformer's current and voltage with the mathematical model of the transformer to estimate the magnetic flux linkage. The mathematical model includes equations for the magnetic flux linkage, voltage and current relationships, and the magnetic circuit's nonlinearity. The AEKF method is applied to a single-phase transformer and a 3-limb, core-type, 3-phase transformer, and simulation results show that it can accurately estimate the magnetic flux linkage even in the presence of noise and nonlinearity. The estimated currents closely match the measured currents, and the errors in estimation are negligible. The paper also discusses a recursive method for developing measurement integrity verification suitable for transformer currents in hardware-in-the-loop, HIL, digital twins, DTs. The proposed method utilizes the Adaptive Extended Kalman Filter (AEKF) to estimate parameters of measured currents and evaluates these estimations using hypothesis tests. Valid estimations are then used in the reconstruction of measurements, significantly improving the performance of DTs. The paper presents several tests to validate the proposed method, including an inrush test and an underload switching test. The results show that the proposed method is capable of tracking currents, even in the presence of noise and nonlinearity. The normalized residuals show abrupt changes in currents due to switching, and the estimated sinusoidal and magnetization components are successfully estimated. The overall effect of the proposed method in improving the performance of DTs is demonstrated through a figure showing the measured no-load current of phase A without additive noises, with additive noises, and the reconstructed measurement at a high sampling rate. The proposed method for estimating transformer current measurements is evaluated using EMTP-RV in Matlab, demonstrating its capability to satisfactorily estimate current measurement parameters and track changes in transformer currents, even in intense saturation. The magnetization current of each phase is decomposed into two components, induced by limb and yoke inductors, which are combined through linear operations to produce functions of the same type as their constituent currents. In the context of hypothesis testing, the null hypothesis posits that the normalized residual is attributed to noise, whereas the alternative hypothesis suggests it is not solely caused by noise. A false alarm is triggered when the residual is induced by noise but is misclassified as being caused by other events. The proposed method is benchmarked against existing digital twin technologies and their applications in power systems, transportation systems, and smart cities. The development of digital twins for power transformers, distribution power transformers, and electric power drive systems is discussed, along with reviews of existing research on digital twin modeling for photovoltaic panels, power transformer remaining life prediction, and fault diagnosis in PEM fuel cell systems. The application of digital twins in power systems is also explored, including microgrid security, distribution network reliability forecast, and transformer fault diagnosis. A comprehensive review of existing research on hypothesis testing, digital twin development, and power system state estimation is presented, covering a wide range of topics, including digital twin technology, power system monitoring, and fault diagnosis.